Hello, everybody. Welcome back. This is going to be Fighting Gerrymandering with PyMC3 with Colin Carroll and Karin Knudson.
Hello. Thank you all so much for coming. I'm Colin. I'm super excited to be here and to give this talk. One piece of trivia I want to mention before I start. The PyMC3 logo that you see up here is beautiful and transparent. And is transparent due to a pull request from Jake Vanderplas last year that he made on the same day as his keynote at PyCon. So we can thank him for the beautiful logo that we can put up here. So this past summer, Karin was taking part in a gerrymandering summer school over at Tufts University and discussing one of the statistical models that they use in talking about redistricting. I'm one of the core contributors on the PyMC3 project. This is a project for doing statistical inference in Python. And it sounded to me like this is something we could implement in 5 or 6 lines of PyMC3. So this talk is really going to be covering sort of the result of that observation. So what we're going to talk about is sort of the history of the Voting Rights Act, which is where this model came from. We're going to talk about what ecological inference is, and then we're going to do some computational experiments with real data. So we took the 2016 North Carolina congressional election, and we did some analysis on it using open source Python tools that are, as far as I know, unique. Great, so I'm going to turn it over to Karin for sort of a discussion of the history and the math.
Hi, I'm Karin. I'm delighted to be here with all of you talking about gerrymandering and PyMC3. This is where I'm coming from very concretely. So this red dot on the map is Andover, Massachusetts. It is the belly of the beast in the original gerrymander. So to gerrymander means to manipulate political district boundaries to achieve certain ends. And the word itself comes from the 1812 district boundaries drawn here by then Governor of Massachusetts, Elbridge Gerry. So if you believe the cartoonist looked a little bit like salamander, and so from Gerry's salamander, we get this wonderful word, gerrymander, that we have today. In Andover, I am the chair of the Math and Statistics and Computer Science Department at Phillips Academy, where I'm teaching a course on gerrymandering this spring. My background, where I'm coming from in that realm, is in mathematics, especially looking at Bayesian models applied to questions of computational neuroscience. So I love useful Bayesian models, which we're going to look at one of later. I should say that I'm not a political scientist or a historian or a legal scholar at all, but I really enjoyed getting into the history of the content and the context of this, and I hope you'll bear with me when we look at some of the history and context in a minute. I think that it's really interesting, it's really important, and it's also key to why you should care about the model and the computation that we're going to show later on. All right, so we will start right here with the Voting Rights Act of 1965. I should say that gerrymandering is a large issue, and what we're focusing on today is particular issues of racial gerrymandering in the context of the Voting Rights Act. So this is a picture from the march from Selma to Montgomery that took place in early 1965, so coming on the heels of the 1964 Civil Rights Act, which prohibited racial discrimination in public places, racial discrimination in the workplace, but didn't go nearly as far as advocates were hoping in terms of voting rights. This is a scene from the very first day of the Selma to Montgomery march, so state troopers attacking the demonstrators in what became known as Bloody Sunday. Bloody Sunday, the events were televised and had a big impact on public opinion, and it was against this backdrop of all of this activism that 8 days later, the Voting Rights Act was introduced into Congress. Later on in the summer, after it had passed in the Senate and the House, Lyndon B. Johnson signed it into law. The Voting Rights Act has been called the single most effective piece of civil rights legislature ever to be passed in the United States. It's going to be helpful for us to have an idea of some of the basic anatomy of the Voting Rights Act. So here we go. Section 2 is what you might expect to see in a Voting Rights Act. It generally prohibits racial discrimination in voting, including vote denial and vote dilution. So this means that it covers not only the blatantly discriminatorily applied poll taxes and literacy tests that were present in the Jim Crow South before its passage, but also more subtle forms of racial discrimination and vote dilution. So including vote dilution in the form of drawing districts such that they would divide up a group of minority voters into multiple different districts, so that a group of minority voters who could have been combined into one district and elect a candidate of choice would not be able to do so. So in gerrymandering, we call this cracking. It's dividing a group up into multiple districts to dilute their power. Its complement is packing, combining, wasting votes by combining, by sort of packing a group into one district. And if you continue the rhyme, there's also tacking, which is another form of gerrymandering. All right. We've also got section 5 here. This is the preclearance section. So this says that districts that were determined to have a history of discriminatory practices in voting were subject to an additional layer of scrutiny. So these are these highlighted jurisdictions on the map here, and in those jurisdictions, when one wanted to change voting procedures, say changing voting locations, redrawing district lines, instituting a new ID law, before those rules went into effect, they had to go through approval by the Department of Justice in Washington or the DC District Court. And Section 4 gave the formula by which the jurisdictions that would be covered under Section 5 were determined. I used the past tense just then because in 2013 we have an important development in the history of the Voting Rights Act. I should say with the Voting Rights Act too that along with this, it's not monolithic. It was reauthorized after its initial passage in the 70s, the 80s, the 90s, and again in the 2000s. So reauthorized, extended, and clarified. In 2013, we have this Supreme Court case, Shelby v. Holder, which rules the coverage formula for which districts will be covered by preclearance unconstitutional. So it technically leaves the idea of preclearance intact, but no jurisdictions are currently covered by this preclearance requirement. It also leaves Section 2 intact. So this is sort of the state of affairs right now. You can still bring Section 2 cases of voter discrimination, but they come sort of one by one, case by case after the fact, rather than this sort of prevention that preclearance provided in certain jurisdictions. Cool. So we're going to look at Section 2 and this class of voter dilution cases. There was helpful clarification that came from both the Senate and the Supreme Court surrounding the 1980s reauthorization of the Voting Rights Act. And let's just focus in on the second of those 9 Senate factors, which is that to successfully argue vote dilution, you need to make a case about the degree to which voting in the jurisdiction is racially polarized. We also have the Supreme Court case Thornburg v. Jingles, and we see 3 factors there. So first, the degree to which the minority group is sufficiently numerous and compact such that you could make a majority-minority district. And second and thirdly, that the minority group is politically cohesive and that the majority group votes sufficiently as a bloc to usually prevent the minority group from electing some candidate of choice. So again, to rephrase, we have another question of polarization that would be something you would need to prove in order to successfully bring a vote dilution case. Cool. So that's what's going to bring us to our question of interest here. This is called ecological inference. It doesn't really have to do very much with ecology, but it has everything to do with polarization by different demographic groups. So here's the idea. We have information on the margins of this table. So we have on the right side demographic information. We know in each precinct something about how many people or what proportion of people fall in one of several demographic groups of interest. We also have election data. We know how many people voted for each of the political parties of interest. And then what we want to figure out is the internal cells here. So we'd like to know something like what percent of people in demographic group 1 voted for candidate A? What percentage of people in demographic group 2 voted for candidate A? So that we can start to build this picture of racial polarization. To make this a very oversimplified but more concrete example, we can say that we have information about, say, the number of black people and the number of white people in each precinct from the US Census, say, and then we also have election information about how many people voted Democrat versus Republican, and we'd like to know the internals of this table again. So things like what percentage of black voters voted Democrat versus Republican, what percentage of white voters voted Democrat versus Republican. And of course, we'd really want to nuance this with more demographic groups and more political groups. And one of the advantages of the model that we'll look at is that it's easy to extend to this case. So we're going to continue looking at the oversimplified 2x2 case, but that's just for clarity of presentation. Rest assured that it's extensible to this other case. All right, our wish list for our inference is we'd like to have accurate estimates. Always something that one desires. We'd like to have possible estimates, right? We'd like our voting rates to be between 0 and 100%. You might think that's modest, but as we'll see, it's something we shouldn't take for granted. We'd like to quantify our uncertainty, and we'd like to make our assumptions explicit. This is where our Bayesian model will be very helpful. And then lastly, we'd like our results to be clearly communicable to courts. This is something that's I thought was really cool. It's not a constraint that I'm used to working with in modeling problems. All right, this is the state of the art for the second half of the 1900s. This is GOODMAN'S ecological regression, was heard as a potential solution to the ecological inference question in different court cases. And the key observation here that we're going to use in the model we'll be looking at is this equation down below the table. So let's just notice that the total proportion of the population that goes Democrat, say, is a linear combination of these coefficients of interest times the census data that we have. So the total percentage of voters that go Democratic is the sum of proportion of black voters who vote Democratic times proportion of black voters plus proportion of white voters who vote Democratic plus times proportion of white voters, and so on. And this is an identity that holds deterministically for each precinct. GOODMAN'S regression basically assumes that the polarization that we see is exactly the same in every precinct, and then performs a linear regression. So a couple problems with this. We really want to know the precinct level estimates for the degree of polarization, which GOODMAN'S ecological regression erases. So that's a bit of a bummer. Another drawback to this method is that it's pretty easy for it to produce estimates like 105% of Hispanic voters vote Democratic, so something that should be theoretically impossible. Yeah. A last drawback, and I love this. This is an expert witness complaining in a case in the 80s that GOODMAN'S ecological regression requires, in all but the smallest jurisdictions, reliance on computers to perform the calculations. So I think this was a few years before Python arrived on the scene, but maybe now, if we're not too bummed out about this particular drawback, we could rely on computers and be all right. Okay, I'm going to walk you through the model. This is stuff that I love, Bayesian modeling, so if you love it too, that's awesome, and please ask questions, find me afterwards. I'll go through it pretty quickly. The thing that I mostly want to highlight is how the equations that we're going to use here to specify the model really translate very intuitively to the code that Colin's going to show you when we look at implementing this in PyMC3. All right, so here we go. At the bottom, we've got our election data. That's that shaded circle there. So proportion, or actually we'll switch to number of voters who voted for a particular party. We're going to model that as being drawn from a binomial distribution with some base rate of success rate of the total proportion within a precinct that goes for a particular party. And again, that proportion comes from this linear combination that involves the census data and our parameters of interest. We assume that we have this for each of P precincts. That's what this little dashed rectangle is is indicating. And then we're going to add a level of hierarchy here. So we want to share statistical strength across precincts that fall in one congressional district. So we're going to assume that we also have congressional district level parameters that control the distributions of our precinct level parameters of interest. And then those congressional level parameters are themselves uncertain, so we will also model them as random variables drawn from their own probability distribution. So this is a model introduced by King, Rosen, and Tanner in 1999 and refined in 2001. Nice things about this are that it produces estimates that are always going to be between 0 and 1, between 0 and 100%. It also makes it really easy to include covariates. So if you want, for example, to include precinct-wide precinct by precinct information on education level or income level or geographic information that you think would affect the polarization rates, you can do so pretty easily. It also extends nicely to having more demographic groups and more political groups. And of course, you can do both of those things at the same time, have more categories and covariates. And now I'm going to turn it over to Colin so that you can see how this all plays in practice and with some real data.
Great. So thanks so much, Karin. So she has the hard part of this talk, going through all the math and everything. I just get to write a lot of code and have some fun with this. So I want to start with a simulation study. So before we get to the North Carolina data, we're going to generate our own data, which has 2 or maybe 3 if you like looking at this adorable puppy, which you really should. His name's Pete. He's really nice. So the 2 benefits we'll have of doing a simulation study first. One is that we'll be able to see all the unknowns, right? So we're going to try to recover some rates that we won't know for sure in the North Carolina data. If we simulate this data first, we'll be able to double check our work. The second benefit we're going to see is that we'll think about our data generating process. And so in any kind of machine learning you do, this is an important step, especially in Bayesian modeling. This is going to be an important step. You want to think about how your data is generated. So there's a lot of notation going on here. There's a lot of political groups and demographic groups. So in the following example, we're going to imagine we're trying to talk about Pete for president. He's an adorable dog. You should vote for him. He's got a simple platform. And we'll just talk about trying to figure out the majority versus minority % of vote for Pete. Who wouldn't vote for those eyes, you know? So simulating data, we're going to use NumPy. So this is numerical Python. First, I'm going to set up a number of precincts. So I chose 14 because that's the most precincts I could display on a single slide for you guys to look at later. The hidden values, these are the values that we're going to want to know later. So this is the % of the minority group that votes for Pete and the % of the majority group that votes for Pete. NumPy, the NumPy random module makes it easy to generate vectors of length 14. The minority vote for Pete will be between 70 and 100%. The average will be 85%. And the minority vote for Pete will be between 0 and 30%. And the average will be 15%. So this is a pretty simple setup. We're assuming that it's going to be polarized, and we should hope that our model can recover that fact. This is observed data. So we're going to be able to see this data from either the census results or the election results. We're going to look at what % of the total population is in the minority group. This is going to be a random number between 0 and 100%. Notice that it could be up to above 50%, so just because we're calling it the minority group doesn't mean it's the minority demographic in that particular precinct. So this will be another vector of length 14. And then finally, the % vote for Pete. So this is going to be this linear combination Karin was talking about earlier. So somehow we're mixing up our unobserved variables, and the goal of our model is going to be to unmix up these unobserved variables. So this will be the % vote for Pete. We'll see that election night. And just to make this neat, we're going to also simulate the voting population as some number between 100 and 10,000. So this will be another length 14 array of integers. And then we can multiply that by the percent voting for Pete to get the actual number of votes for Pete in each precinct. Okay, so we've got a bunch of vectors of length 14. And then we can go, that's where it comes from, then we can go plug this into PyMC3. I'm not going to go over much about how PyMC3 works or models, but I just want to show you, put this up here in sort of purposely small font, so maybe you can squint and see some of the distributions that Karin was talking about earlier. The other thing I want to emphasize here is that, well, you can't see, but the very last line is pm.sample. And that's all you call, and there's just a lot of pretty cutting-edge statistics and algorithms going on behind that one function call. Thomas Vicky, one of the other developers on this project, calls that the inference button. And so it lets the developers who are thinking about how to do this well come up with the right way to sample from your model. I also want to mention on this slide that until about 5 years ago, it would have been impossible for a general purpose language to sample a model like this. So there are some interesting algorithms developed in 2013, and PyMC3 is one of the implementations of this algorithm in Python. So if you really want to do cutting-edge statistical inference, PyMC3 is a great choice. Great, so what's the output of a PyMC3 analysis? If you're familiar with scikit-learn, if you're familiar with deep learning libraries, you'll often input points, and you'll get out points as your estimates. In PyMC3, in probabilistic programming, you're using probability distributions as your input, and you're getting probability distributions as your output. And so what we're actually going to see here is a distribution of predictions. So I've plotted here in red the estimated percent of the majority demographic that votes for Pete. The dotted vertical line is the true value. That's the value that we won't see in the North Carolina data, but we can see because we simulated the data ourselves. So you can see it's not exactly at the peak, it's near the peak, and that's because the histogram that you're viewing there is essentially likely scenarios for, that would cause the data that we observed to happen. So what PyMC3 did was it went through and it simulated, in this case, 5,000 different worlds that might be reasonable given the data that we observed and the model that we specified. I'm going to plot also the minority demographic vote for Pete on the same axis. So you can see here again, it was pretty close to the peak of the distribution. If you're using a library like scikit-learn or like some sort of deep learning library perhaps, you would typically get the peak of these distributions, and that would just be a single point as output. That would also be much faster than using PyMC3. So the reason we're using PyMC3 here is because we want to reason about our uncertainty about these estimates. So the fact that we get these histograms is a feature. And now I said we had 14 precincts, right? You can't really gerrymander just with one precinct because then everyone gets to vote. But here we've got 14 precincts, and I'm showing you the estimates that our model gets, King's model gets really, over all 14 of these precincts. And so you can see often it ends up near the peak of the distribution. Sometimes it doesn't. Sometimes we're a little bit surprised, but usually we're not that surprised by what the true value was. And what I want you to take away from this slide is that when we go forward and see the North Carolina results, we think this is a reasonable model. Sometimes we're pretty uncertain about things. You know, in precinct 6, we're pretty uncertain about where the true vote might have been, but at least it's directionally correct. Great, so I want to go and talk about the actual data, the real data. We're using 2 big data sources for this. Open Elections, which is a wonderful project. It's working in Python, and they're collecting precinct-level election results for all across the US. It's really incredible. And the other source is the US Census data. I think that's a more popular data source, and it's just a treasure trove. The 2 of them don't talk to each other very well. So the census blocks and the precincts do not match up very well. So in the repository that we'll distribute for this talk, I've got a manual labeling of a lot of the census blocks back over to precincts and the precinct level labels. But this was very much my experience when we were first trying to do this. I figured it would be, you know, an hour or 2 in the afternoon and we'd be all done. But geographic joining is quite messy. I also want to call out Open Elections for the great work they're doing. So these are some of the pictures they've sent out of the precinct level results they've gotten. On the left is Litchfield, Connecticut, which is where my parents live. And the handwriting on these election results looks suspiciously like my mother's. So I'd like on this Mother's Day weekend to give her a special shout out. I don't think it's actually her, but you know, it gives you pause. And this on the bottom is especially impressive. So this is some election results from Texas, I believe, and it's a picture of a spreadsheet embedded in an Excel spreadsheet. So that's just an incredible level of dedication to like data obscurity. So at the end of the day, after doing all this manual labeling, I was able to match up about 6.8 million out of the 7.1 million voting age people in North Carolina, and find about two-thirds of the votes. Most of the votes that are missing were absentee or mail-in ballots, which don't belong to any individual precinct. So we would have to think more about how to involve those in the model. What I've got up here is a map of North Carolina with the congressional districts drawn. You'll see some little islands of lines in there, and those are the precincts that are missing from my data set. So that was just not being able to match up the census with the precinct level data. We can layer on the precincts onto this. So we had about 2,600 precincts in our data set, and we're going to have estimates for each of those. And I should mention that in King's original paper, he did this for 260 voting precincts. So we're about an order of magnitude bigger with the amount of data we're working with here. And just to give you another idea, this is the end result. Blue is that votes for Democratic candidates, and red is voting more for Republican candidates. We did just omit third-party voting in this analysis, which I invite everyone to give us a hard time for later. But so this data is very easy for you to get and to see. The last thing I want to say before I show the end results of running that same PyMC3 model is exit polls. So there is no exit polling for congressional data. This is for the governor and the Senate race, and there's only 5,000 people interviewed. So this is not some place where you could recover the analysis we're doing for all 2,600 precincts. However, directionally, you might expect to see 75% of non-white voters vote Democrat, and about 35% of white voters vote Democrat. So without further ado, this is that ecological inference model. This is on North Carolina 1, and I'm just showing a random sampling of 14 precincts. So you can see here it was quite divided. We had some amount of uncertainty over the white vote in a couple of these precincts. You can see it's really spread out. But the non-white vote is often very close over to 100% for the Democratic candidate. This one went in a big way for the Democratic candidate. Here's another precinct or another congressional district that also went Democrat. You can see here every single non-white precinct we found, we were estimating was almost entirely voting for the Democratic candidate, whereas the non-white vote was more towards the middle. This was a landslide Republican congressional district, and you can see there's a lot of uncertainty over the non-white vote, but the white vote was very much clustered around 0% for the Democrats, or let's say under 20%. And the last one, this was actually the closest race in North Carolina in 2016. So this was decided by 12 points, and you can see that the non-white vote was very much clustered up above 90%, whereas the white vote was sort of spread out a little bit more. Great, and I want to finish up with just going back to a summary of the analysis that was done. So this was, again, the election results, which you could see on CNN the night that the election happened. This is the percentage of vote that went, this is the election results if only non-white people had voted. So you can see it's just overwhelmingly Democrat. You can look, if you look closely at some of the congressional districts, you can see the artifacts of the hierarchical modeling. So I think especially out in West North Carolina, you can see that that's a little bit lighter. And that's because we assumed all the precincts were being drawn from the same distribution. And similarly, this is the white vote that we were estimating in North Carolina. So again, very much not for the Democratic candidate. And as far as I know, these are novel maps of the most sort of granular maps you can find of racially polarized voting. Great, so just to conclude, now's a great time to be thinking about redistricting and thinking about gerrymandering. There's a census coming up in 2020, after which they'll be redrawing the district lines. So yeah, thanks so much for coming. There are slides up online, and we'll be happy to take questions out in the hallway afterwards.
Thank you to Colin and Karin, and as I said, they'll take questions at the back, so thank you.